What is going on, guys? Welcome back. In this video today we're going to talk about the set cover problem, and we're going to implement two different Python algorithms to solve it. So let us get right into it. Alright, so we're going to learn about the set cover problem in this video today, and we're going to implement two different algorithms in Python in order to solve it. Now, the set cover problem is a classic optimization problem similar to the knapsack problem that I recently made a video on, or similar to the TSP. It's actually quite simple and easy to understand. However, it's not easy to solve because it belongs to a class of problems called NP-hard. And what NP-hard basically means, practically speaking, is we don't know any efficient algorithm that is guaranteed to find the optimal solution to a problem instance of the set cover problem. So if I have the set cover problem, any set cover problem, I don't have a polynomial time algorithm that guarantees to find the best solution. Now, we can have fast algorithms that find a good solution, probably, but we don't have algorithms that are guaranteed to find the best solution. Now, the set cover problem, let me briefly explain it to you, is, as I said, quite simple. We have something called the universe, and the universe is basically all the elements that we have in this example. So, for example, this could be a set 1, 2, 3, 4, 5, 6. These are all the elements in our universe. And then I have a number of sets, and these sets contain elements from the universe. For example, one set could be 1, 2. Another set could be 1, 3, 4. Another set could be just 2. Another set could be just 5. Another set could be 5, 6, and so on. We can have different sets, and the goal is now to use sets from the sets that we have. Now, we don't have unlimited sets. We don't have all the sets necessarily. We have a certain number of sets given. For example, in this case, we have these. And the question is now, how can I cover the whole universe? So how can I cover all the elements by choosing sets and minimizing the number of sets used? So for example, in this case, what I could do is I could go with 1, 2. I could go with 1, 3, 4. I could go with 5, 6. So I would use 3 sets now. I used 3 sets to cover the whole universe. Why does this cover the whole universe? Because I have 1. I even have it twice, it doesn't really matter, but 1 is part of my set union here. I have 2, I have 3, I have 4, 5, and 6. All the elements of the universe are covered, and I used 3 sets to do that. What I could have also done is I could have gone with 1, 3, 4, then with 2, and then with 5, 6. Or I could have also gone, maybe if I have another set 6 here, I could have also said 1, 3, 4, like this, then 2, then 5, then 6. Now I would have used 4 sets. So this solution and this solution, they are better, but this is also a valid solution. It's just not the optimal solution. So the optimal solution is to cover the whole universe, to use the sets that we have here, to cover the whole universe with as few sets as possible. So I want to minimize the number of sets used to cover the universe. That's the idea. And this, as I said, is a simple problem to understand it. It's not that simple to implement it, or actually the implementation, the idea behind the implementation is also not too complicated, but you cannot do that efficiently, because if you have a large universe and a large number of sets, it's not really possible to find the best solution efficiently. And we're going to take a look at that here. We're going to start with the coding. We're going to say import random so that we can generate some problem instances, and we're going to go with import iter tools. We're going to need that for the combinations. So iter tools, there you go. And the first thing we're going to do is we're going to define, or we're going to create a function that is going to generate our problem instance. So the idea is we want to generate a universe of a certain size, and then we want to get random subsets, and we want to make sure that the subsets can actually cover the universe. So we want to make sure that we actually have subsets that can result in a solution to the set cover problem. So we're going to say generate universe and subsets. Let's call it like this. We're going to pass to this function the universe size. We're going to pass to the function also the number of subsets, the minimum number of subsets. We can also exceed that number if necessary. And we are going to say minimum set size and maximum set size, just so we can play around with these parameters a little bit. And the basic idea now is I can say the universe is just going to be the set of numbers that range from 1 up until the universe size plus 1. So if I pass 50, it's going to be 1 and 51, which will generate the numbers 1, 2, 3, 4, 5, and so on up until 50, because the last number here is not included. So this is going to be my universe. And the subsets, we're going to start with an empty list, and we're going to say that we have remaining elements. So elements from the universe that are not covered yet. And in the beginning, this is going to be, of course, the universe itself. None of the elements are covered, and we don't have any subsets. And then we're going to say while we still have remaining elements, so while the universe is not completely covered, what we're going to do is we're going to say the set size is going to be equal to random randint. We're going to generate a number between minimum set size and maximum set size, so that we have different set sizes. And we're going to say that the new subset that we consider adding to the list is the set of random.sample. So we want to sample randomly from our universe, or actually, in this case, since we're aiming to cover all of the remaining elements, we're going to just sample from the remaining elements, which in the first iteration will be the universe. But then when we get the elements, when we get some elements covered, we're only going to sample from the uncovered elements. So we're going to say list remaining elements, and then we're going to say here minimum set size, or if the set size is too large, we're going to sample, because maybe we only have one remaining element and the set size is 5. In this case, we want to go with the length of the remaining elements, if that's the smaller number, right? That's the idea. So now we have a new subset. We just sampled a certain number. So either the random set size that we generated up here, or all of the remaining elements here. And we create a subset based on that. We append this subset to the subsets list. And then what we do is we subtract the elements from the remaining elements list. So the idea is if I have, for example, as we said in the example, 1, 2, 3, 4, 5, 6, and then I sample, for example, 4 and 6, then my remaining elements are for the next iteration 1, 2, 3, 5, and from those I'm going to do the sampling again. Maybe I sample 3 elements this time, 2, 3, 5, and then I have only 1 element remaining. So if I somehow generate here for the set size 5, but I only have 1 element left, of course I'm just going to go with this. That's the idea, because we want to guarantee that the universe is covered. This is why we artificially create this problem instance like this. And in addition to that, we also want to have some random samples from the universe that are not artificially crafted to cover it. We just want to have some random subsets as well. So we're going to say for placeholder in range, and we're going to go number of subsets minus the length of the subsets that we already have. So we want to only add new subsets if we have not exceeded the number of subsets. Now the problem is, of course, or it's actually not a problem, but the thing is, if I need more subsets here to cover more than I have passed, of course I'm going to exceed that number. But I'm not going to add additional subsets, additional random subsets, if that's the case. But we're going to set that number high so we can actually find multiple solutions. So we're going to say set size is equal to random.randint here as well. We're going to say, again, minimum set size and maximum set size. And then I'm going to say new subset is equal to set random sample from the universe now, actually from list universe, because the sample function I think on sets is deprecated. So we sample from the universe the set size. This time we don't need any minimum because we're going to have the full universe. And then what we're going to do is we're going to say subsets append new subset. Quite straightforward. And then we're just going to return the universe and the subsets. So this is just for generating the problem instance. This is not anything with set cover yet. This is just getting, this is just getting the problem instance so that we have something to work with, so that we can run it multiple times without having to manually create an example here. All right, so what we want to do is we want to say universe and subsets is equal to generate universe and subsets. We're going to go with a universe of size 60. We're going to go with 25 subsets, let's say, or actually maybe let's go with 20 subsets. Let's go with a minimum set size of 5 and a maximum set size of 15. And then we can actually go ahead and print our universe and print our subsets just so we can see what they look like. Maybe let's go and say for subset in subsets print S. That's the idea. This is our universe, obviously just numbers from 1 to 60. And these are now our randomly generated subsets. All right. So every time I run this, we're going to get a different problem instance, obviously. All right, so the question is, how can we now find the optimal solution? And also, what is the runtime complexity? Now, the optimal solution, as I said, cannot be found in polynomial time. So it cannot be done efficiently. We cannot get an algorithm that guarantees us the best possible solution that runs in polynomial time. But we can still come up with an algorithm that will give us the best solution. It's just not going to be an efficient one. It's going to have exponential runtime. And this is, of course, the brute force solution. So brute force set cover will just go through all the combinations until it finds one that satisfies the problem or satisfies the condition. So we pass the universe and the sets, and then all we have to do is we have to define how many sets do we have. And all we do then is we go and iterate from I in range. We go from one set that we use up until n plus 1 again, just so we can get to n. And we ask ourselves, what kind of combinations do I have for subset in itertools dot combinations of the sets with I. What this basically means is, I'm gonna show you an example here in a second. Actually, let's do it right away. Pass. If I have now again my universe 1, 2, 3, 4, 5, 6, what this means is that in the first iteration I will be 1, which means we're gonna go through 1. Or actually, we need some subsets. Let's go. We have 1, 2. Let's go. We have 2. Let's go. We have 3, 4, 5. Let's go. We have 1, 3, 5, and then maybe we have 5, 6, and maybe we have 1, 6. I don't know. Whatever. What this will do is it will go through the sets here. So this is S, and this is the universe. And it will try using just one set. Can I cover the universe? So it will try 1, 2, it will try 2, it will try 3, 4, 5, it will try 1, 3, 5, 5, 6, 1, 6. It will see, okay, I cannot cover the universe using one set. So what I'm going to do is I'm going to go through all the combinations of sets using 2 sets. This is when we increase I. Here now we're looking for combinations of sets when I use 2 sets. So it will do this, 1, 2, and 2. 1, 2, and 3, 4, 5. 1, 2, and 1, 3, 5. 1, 2, and 5, 6. 1, 2, and 1, 6. And then it will go 2, and 3, 4, 5. 2, and 1, 3, 5. 2, and 5, 6, and so on. Then it will see, okay, I can also not cover the universe using 2 sets. So I'm going to increase I, and I'm going to try with 3 sets. And then it's going to, at some point, stumble upon, or it will stumble across the 1, 2, 3, 4, 5, and then 5, 6, for example. And then it will say, okay, I found a solution. It's the best solution because there is no solution with 1 set. There is no solution with 2 sets. The reason I know that is I tried all of them. None of them works. So the best possible solution has to have 3 sets if I find one with 3 sets. That's the basic idea. That's brute forcing it. So we go through all the combinations, increasing the number of sets used. And if at some point the set union of, and now we're going to unpack the subset. This is basically just taking the subsets, combining them all together. If this union is equal to the universe, we just return the subset. That's it. That is our, I forgot the if statement here. That is our basic brute force algorithm. So again, the logic behind it is simple, but the efficiency is not. So we can go ahead and we can say brute force set cover universe and sets. Actually, yeah, subsets. And this is going to return the solution. And what we're going to do now is we're going to say print universe, print subsets, or actually let's go for s in subsets, print s. And then we can say print the solution, then also print the length of the solution, and also print if the solution is equal, or actually not the solution, but if the union, set union of the unpacked solution is equal to the universe, to see that this is actually a valid result. And you can see now, this is our universe. We have these subsets, and our solution in this case is this. You can double check this on your side when you run the script, but this is a solution of size 8. This is the best possible solution. It's guaranteed because we tried all the combinations, and it is a solution. And I can run this multiple times. You will see for different problem instances I get different solutions, obviously. But this is guaranteed to find the best solution. Why is it inefficient? Well, we can do a basic runtime complexity without making it too complicated. The number of combinations, if you think about this, every set can either be part. This is the same that I showed you in the knapsack problem, where we also went through all the combinations. For every possible solution, a set can be included or not included. So every set can be either 0 or 1. And then for this 0, 1, every other set can also have this position of being 0 or 1. So basically you have 2 to the power of n possibilities, because every single element can either be included or not. You multiply all of this together because you have to consider all the possible branches. You get basically in a runtime complexity of O of 2 to the power of n, so it's exponential runtime complexity. Now, of course, you have some operations in here. You can probably multiply this with some constant here. It doesn't really matter because at the end of the day, this is just an exponential runtime complexity. This dominates 2 to the power of n. So this is exponential runtime complexity, which is by definition not efficient, because you will see if I just run it like this, it's quite fast. If I increase by 1, if I increase the number of subsets by 1, it's still quite fast. If I do this again, at some point, at some point this should get quite slow. Let's try with 25. Actually, still quite fast. Let's go with 30. Still quite fast. Let's go with, oh, actually, no, this is not a good idea, because what I should do is I should probably allow for more sets. Okay, this is now a bit too much, I guess. The thing is, increasing the input size, increasing the universe size, or the number of subsets massively slows down this algorithm. So more n, or more m, depending on what you want to call what, so the universe size or number of subsets, increasing these massively increases the runtime. And this is not the case for polynomial runtime, because that's the definition. You know, if n is your variable, if you have it in the exponent, that is super problematic, because if I have 2 to the power of 20, for example, that's a huge number. But 2 to the power of 21 is already a much larger number. 2 to the power of 25 is a huge number. So the growth is very different than if I have, for example, this number in, if I have it the other way around, if I have n squared, so n to the power of 2. Because if I have 20 to the power of 2, and then 25 to the power of 2, that's not that much of a difference. It's not huge. It's quadratic complexity. This grows exponentially. It's huge. That's the basic idea here. So it's inefficient. Let's leave it at that. Now, what we're going to do now is we're going to implement a heuristic. We're going to implement a greedy approach. And the basic idea here is we're going to find a solution quickly. We're going to probably find a decent solution, but it's not going to be the best solution. At least it's not going to be guaranteed to be the best solution. So we're going to say greedy set cover universe sets. And what we do here is we just pick the set. So we again construct the same thing. We have uncovered is going to be just the copy of the universe. So nothing is going to be covered by default. Obviously, we have the subsets, or actually let's call this solution. It's going to be an empty list. It's going to be empty in the beginning. And what we do is while it's not covered, while our universe is not covered by the sets, we pick the next best set. Now, what is the next best set? It's defined as maximizing, given the sets, using the following condition. We're going to use a lambda expression here. Given a set, we want to get the maximum length of S and uncovered. What this basically means is, this is maybe a little bit not counterintuitive, but maybe not easy to understand. The basic idea is we have a bunch of sets that we can choose, and we have elements that we have not yet covered. We want to find the set that when you combine it, when you get the intersection of all the elements that we need to cover and all the elements that this set covers, that we get the greatest possible intersection. So let's say we have these elements here are missing, and I can choose between this set and I can choose between this set, for example. Now the union, the intersection of this set and this set, or actually let's do it like this. This is a good idea. Let's do it like this. The intersection of this set and this set is this. And the intersection of this set and this set is this, because we cover more new elements in this one. And the length of this one is 4, the length of this one is 2. We're trying to maximize this length. This is what we're doing here. And this is our best set. This is the greedy approach. Not necessarily the best approach, but the greedy approach. And then we say, we select, or actually, we say solution, append this best set, and then repeat the same thing. Of course, update the uncovered, subtract from it now what we have added to our solution. And when we're covered, we just return the solution. That's the greedy set cover. So we can actually go ahead and just copy paste this. You can say greedy set cover, and I'm actually gonna run this. Let's do it like this. Let's take this and run this after the greedy solution and see how much faster it is. So if I run this right now, you can see, or maybe it was not that easy to see. Let me just go ahead and not print the universe, not print the subsets, just print the solution and the length here as well, like this. Now you can see I get the greedy solution immediately. It takes quite some time to come up with the brute force solution. I hope we're going to find it soon, because the thing is, the later you find it, the longer it's going to take. If the best solution has 5 elements, you're going to find it quite quickly. If you have to go to 10, like in this case, you will need much more time. And when we analyze the runtime complexity, we don't care about some best case scenario. We always care about the worst case scenario. And the worst case scenario is exponential time. Of course, you can find a solution with one set already. Then you have it instantly. But that's not the worst case. The worst case is you have to go to the maximum number of combinations. So the worst case is you have to go all the way up to the universe size, because maybe your universe is 1, 2, 3, 4, 5, and your sets are 1, 2, 3, 4, and 5. In this case, you will have to go to the end, and that's the worst case, and that's what we care about when we analyze the runtime complexity. All right, so you can see, or you saw, that this gave us 10, this gave us 11. This was done instantly. This took some time. I can run this again. We get 9 instantly. We get 8, which is better, but we take some more time. And of course, I can do this again, 6 and 6. Now it's got the optimal solution as well. 10, so 10 is now what I get instantly. 8 is what I get from the brute force solution, which is better, but it takes some more time. And of course, this is a very small problem size. If I go with something like universe size 80, if I go with number of subsets 50, if I go with 2 to 15, I can run this. I get this immediately, 12. I get a solution of size 12. Now, this will take quite some time, probably, for our brute force algorithm to do that. And if I increase the numbers, the greedy heuristic will not have a problem. If I go to 200 probably, and I go with, let's say 60, or let's say 80 subsets, and I go with a max size of 25 maybe, I will get an instant solution of size 17. This will not be done that quickly with the brute force. I can even increase this more. I can go to 500. I can go to 150 subsets. And I will still get it instantly. 41. To get to this solution takes forever if you use the brute force approach. It will not be possible. Probably I can run this for a very long time and I will not get a solution. So you can see I will not necessarily get the best solution. Maybe the best solution is not 41. Maybe I can get it done with 30. But I will get it instantly with the greedy set cover heuristic, and it will take forever if I do it brute force. So I can get the best possible solution in exponential time. I can get the quick, good solution in what time exactly? Let's analyze this. So how long does this take? Basically, think about it that way. This operation here tries to find the maximum of the set. So you have to iterate over n sets. If n is the number of sets, you have to do this in O of n, because you have to go through the whole list. It's in linear time, maybe times some constant, whatever you have to do here. But you have to go through all the individual sets to find the best set. This is linear time. Now, the question is, how often do we have to iterate here? And in the worst case, what I have to do is I have to go through the whole universe. So in the worst case, I have to go with O of m, so linear in terms of the universe, which leaves us, basically, if we ignore all the constants, basically we just have to multiply this. So it's O of n times m runtime complexity, which is polynomial, because it's like n squared, but we have universe and sets. That is a polynomial runtime complexity, and this basically means that this is an efficient algorithm to find a solution, even though it's probably not going to be the best one. We can actually try to take this to even higher values. Maybe if I go 5,000 and 250, there you go, 369. To find this solution, or a solution of this size using the brute force approach, will take forever. It will not be possible. Probably I can add a 0 here and a 0 here. It won't. Oh, actually, it does make a difference. It makes it a bit slower. So let's see if we. I mean, you still have to consider it is growing in complexity, and it is growing quadratically. Oh, there you go, 3,687. It is growing quadratically, not linearly. So it's not like there's a gradual growth. It's still quadratic. It's still polynomial, but it's way better than exponential. I will not get a solution at all with this problem size if I run the brute force approach. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting a like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video, and bye.